Okay, Beidi, good luck.
Yep.
Oh, I was just waving, but you couldn't see anymore.
Yes, I will just share my screen now. And can you still see my slides?
Yes,
Yes.
yeah, we can, yeah.
Yeah, perfect. And I will also start a watch. Yes. So thank you very much, everyone, for joining. So I will be defending my thesis that is titled Answer Set Programming for Building Information Modeling, or ASP for BIM for short, in the next 40 minutes. And why did I choose this as my PhD research topic is that I have backgrounds in mathematics and building technology. And in this presentation, I will be combining those domains in the field of automated building code compliance checking, which is that we take a building model and we want to assess its compliance with respect to building regulations. First, a motivation of why this research topic is relevant and interesting is that, so as you can see in this video, is this video playing? Yeah, so you have a window, but when you open this window, it clashes into a radiator. So when we want to represent this kind of scenario schematically, we have a window, we have a radiator, and when the window is opened or closed, it spans over a quarter of a cylinder. And a person will also need some clearances around the radiator knob to turn it on or off. But those two spaces clash. And this is a very common issue in building design, because when the building is undergoing different stages of design modification and refinements, the design requirements are not documented and communicated, but only the physical models which contains the physical manifestation of a building. So an architect might be placing a window because they want to optimize daylight or facade. But when the design is passed down to the engineer, they add a radiator which provides heating to the space. And when the design is finally passed down to the contractor, they might reorient the routing, they might reorient the radiator to facilitate routing, for example, which eventually leads to this very trivial design flaw, but nevertheless was undetected during the whole design process. So my hypothesis of the PhD thesis is to say that design requirements can be indeed documented because they naturally already exist in building codes, and especially performance-based building codes, which talks about how humans experiences space, what are their needs and what are experiences, etc. So we have a building regulation, but we need a way to represent people and space and also affordances that are elicited in those regulations. And on the other hand, design requirements can be indeed communicated as formal constraints that are also that adhere to the data standards, so they can be delivered together with the building model. But we still need a way to reason systematically about form, orientation, and topology, so design requirements can be encoded as lower level geometric or topological constraints. And so what does ASP for BIM do? It's a declarative spatial reasoner, which is enhanced with domain knowledge about people's perception and action, but also objects' behavior and function. So we can interpret design requirements, and we can also enrich building models according to those background theories that we have about people and space. So some highlights of the major research findings that will be shown later on in this presentation. That the first case study was a requirement that talks about the visibility. Bathroom objects should not be visible from access routes. And ASP for BIM is evaluated on a large scale, sorry, let me just put this, on a large scale building model with 2 stories with more than 8,000 BIM objects. And ASP for BIM identifies 4 problem areas, where the visibility space of a bathroom objects overlaps with the movement space of people. And ASP for BIM does this in only half a second. The second case study, is about a design requirement that guardrail systems are needed at leading edges of a building. So in this case, we also evaluated ASP for BIM on a building, on an 11-story building with 250 BIM objects, that, which also contains a construction plan that is made of 122 time steps. So ASP for BIM in this case runs in merely 2.3 seconds, and it generates plenty of what we call spatial artifacts. There are implicit objects that enrich semantically a BIM model. So in this case, for example, leading edges correspond with 4 hazard spaces. They're the intersection between regions where people can reach, so movement spaces, and regions where people can fall and injure themselves, which are fall spaces. Right, so the main body of this presentation is will be led by kind of a roadmap that I made. So first, I would like to introduce some fundamental concepts in this research, because I'm expecting that the audience will be kind of mixed, that some people know a lot about BIM, some people know a lot about logic programming. So building information modeling, or BIM, provides sort of a mapping between physical building and digital models. So in an actual building, you have components, and they are represented formally in the digital model as objects, and their materials and connections will be formally represented as attributes and relations. And BIM has an underlying exchange format or data standards that's called Industry Foundation Classes, or IFC for short. So IFC is an entity relation model, which if we represent an IFC file graphically, then it's like we have objects, we have their relations attributes, and they're represented as nodes, and they're connected by edges. So when we have the BIM model, we might want to ask some questions. For example, where is the nearest bathroom? And nearest here refers to distance. Bathroom refers to some kind of semantic information about models, about building models. Or we want to ask, is this bathroom accessible to wheelchair users? And in this case, accessibility is a concept, is a qualitative concept that is open for interpretation. Or we might also want to ask, do all bathrooms meet all requirements? And thus, we want to reason about those questions, but how? Which leads to my 3 major research questions. The first one is, how do we declaratively query semantically rich building models with complex geometries? And declarative here refers to the fact that the query should not depend on how information about buildings is structured, and the query should remain the same if the building model is updated or changed. The second research question is, how do we objectively analyze a building's performance in supplying occupant needs? Meaning that many human-centric concepts about performances are ambiguous and vague, but we need to associate them with some quantitative metrics. But how do we do this with the least of bias as possible? The third is that how do we consistently and efficiently check many building objects against many code requirements? And this again refers to the fact that we want our compliance reports to be explainable, that it's consistent with our common sense about space and people, and they're also motivated by research studies. So this is the topic of automated building code compliance checking, and what is the solver that we need that takes in design requirements, that takes in both building models and generates some kind of compliance reports. So if we take the golden approach that is proposed by Eastman in 2009, we have 4 stages for code checking. So if we take a requirement that says all patient rooms shall be visible from the nurse station, and then we might want to check a nurse station and a patient room that are located on the same floor, that share the same corridor, and we compute some line of sight. But this obscures the true semantics of the requirement, because we're adding two additional assumptions that for patient room and nurse station to be visible, they must be located on the same floor and they must share a common corridor, which are not always the case. And so this creates a huge problem of mixing problem definitions with runtime concerns, which makes the whole solver engine less modifiable and less maintainable. And the idea of ASP.NET in tackling those challenges is to push down runtime concerns into the solver so a user can express what they want their problem very declaratively without worry about how the problem gets solved. So for example, we can formalize design requirements as very simple logical rules, which provides a clean and verifiable encoding that everybody can check if the semantics are correctly translated. And on the other hand, we have built-in models and we can use deductive rules to infer implicit properties from this model, which also provides a transparent and traceable reasoning way of reasoning about building models. And last, so ASP.NET has many domain knowledge integrated, so it knows how to interpret quantitative concepts such as visible. So it says that two objects are mutually visible if they belong to the same visibility graph and they're connected by the same edge. And in this case, ASP.NET has built-in very general data structures. So again, to separate runtime concerns from the pure definition of the problem. But we have some challenges, as requirements are ambiguous and vague often, and models are inaccurate and imprecise, and domain knowledge about space and people are implicit and disparate. So how do we tackle them? First, let's talk about the first research question. Why do we need declarative spatial reasoning? So if we consider traditional software where a user specifies some program which gets executed in a computer, answer-set programming provides another paradigm where the solver is enhanced a priori with expert knowledge. So that talks about human common sense, about space, about objects, best practices that are applied in the building industry, or research evidence about how people perceive or act upon space. So in this way, a user can just use facts, rules, and constraints to express, to define an ASP logic program. So ASP, a bit of semantics, which is very, kind of just a general concepts to logic programming. But ASP in addition is three-value logic programming, which means that a user can express that P is true, P is false, or the truth value of P is unknown, which makes it much easier to retract and revise knowledge as we acquire new information about the real world. And secondly, ASP has stable models, which are problem solutions to a larger program that composes of facts, rules, and constraints. So a very concrete example, we have a wall and we have a window. The window is hosted by the wall. So we can kind of translate this IFC graph or this formal graph into a series, a list of ASP facts. And we can use deductive rule to say that if the window is indeed hosted by the wall, that we know that the window is dependent of the wall. Or alternatively, we can assert facts by default to say that if we don't know anything about the swing direction of the window, then by default, we assume that it swings to the left. We can also use choice rules to compute hypothetical scenarios of a building. So in this case, we can assign any time step from 1 to 3 to a window, meaning that the window can be constructed at time 1, 2, or 3. But it's not always possible because we have an integrity constraint that says if the window is dependent on a wall, then the window must be constructed after the wall. In this case, we eliminated the other two models, and so the window can only be constructed at time step 3. So ASP for BIM, on the other hand, it has a declarative problem instance. And on the other hand, ASP, so from now on, I've shown that how to reason about buildings in ASP symbolically. But I also want to reason about building models in ASP, which is linked to extensive numeric data. So the way to do this is I have enhanced ASP with spatial theories, and especially spatial functions and relations and data structures. So on the other hand, on one side, you have a symbolic logic program, but predicates in those programs can be referring to some numeric data or external computations. So in this way, ASP for BIM generates some deduced facts, some asserted facts, and some tentative facts, which are derived from the problem instance and also consistent with the background theory about space. Right. So the second research question is that how do we interpret and implement and formalize and parameterize a building's performance goal? So if we consider the requirements are often ambiguous and vague, then we have I went too quickly. Then, for example, we take this code that says ramps shall be able to be used by people with limited mobility. And what is usability is a very qualitative concept, but it should be interpreted and quantified based on with respect to specific type of user, specific type of occupant and action and situation. So usability, safety, or comfort can be linked to quantitative metrics such as width, slope, or surface friction factor. And those kind of disambiguation will be motivated by research studies about anthropometrics, ergonomics, proxemics, or cognitive psychology. So they're evidence-based and therefore they're more objective. And the second challenge is that building models are inaccurate and imprecise. And so, for example, this code talks about accessible routes and principal entrance, but what are these concepts? Then, for example, we can use non-monotonic reasoning. The first one is default reasoning, that we can assert that an accessible route, a space, is accessible if we don't know that it's not inaccessible. Or otherwise, we can say that based on this code regulations, we know that a space is definitely not accessible if it doesn't meet the minimum clearances requirements. And in this case, went too quickly. And so in this case, the minimum clearances will depend on whether the door opens inwards and outwards. But what if this kind of information is missing in a BIM? Then we can use hypothetical reasoning to counterfactually complement the incomplete building models with additional facts that will lead to our goal. So in this case, we do want the accessible route. We do want the states to be accessible, but we don't know about the swing direction of doors. So if all doors swing to the right, then we can clearly see here that clearances are not met. So this will not be compatible with our goal. But if all doors swing to the left, then we do have the clearances requirement met. Right. So now that we talk about design requirements and building models, some concepts like line of sight or access route, and they will be mapped to enhanced building objects such as visibility space and movement space. So I will be talking about now occupant modeling. How do we do that on a very, very concrete case study? So take this design requirement again that talks about privacy of bathroom objects, so they should not be visible from access routes. We have, so no fixtures, no bathroom objects can be located below the vision limit line. And we define first a concept that is functional space, so regions that a person needs to be located in order to use an object. Yes, so we have a lot of research studies about what how functional spaces should look like, and their shape will eventually depend on who are using those objects and how are they using them. So the shape of functional spaces can be derived step by step by first taking the bounding box of a bathroom object, then scale it, and then translate it perpendicularly to the hosting wall. So eventually you have a functional space with the exact dimensions as prescribed by the research evidence. And then we can compute the visibility space of this functional space, which are regions where this functional space is visible. And again, the shape of this visible space depends on the occupant, their eye level, their visual range, but also on the environment, whether there's any visual reflections, whether there's any crowds. So computationally, we can compute the isoburst of an object, but then we can clip this isoburst by a visual range of 50 meters to say that, okay, only within this region, the object's actually visible. Or furthermore, we can clip this visibility space, we can compute the circular sector of this visibility space of 160 degrees to say that only within this region, the object is not only visible, but legible. Right, so now we move on to movement space, which roughly corresponds to the notion of access route or access routes. Again, the shape of the movement space depends on occupant, their body height, their shoulder width, and also on situations, whether they're queuing, whether they're evacuating, etc. So in this case, the movement spaces is computed again, kind of chronologically using a constructed solid geometry approach. So first we take the difference between all slabs and all walls, which gives us topologically disconnected rooms, and we then connect those rooms by transitional objects such as doors, which gives us movement spaces. So this rule is eventually interpreted as movement spaces and visible spaces should not intersect or formally with a spatial predicate, which is called intersect, that will be integrated into ASP for BIM. Yes, so when we evaluate the performance of ASP for BIM on a number of code provisions from New Zealand that talks about privacy and accessibility, we get we get very fast run times that ranges from 0.2 seconds to 8.4 seconds on this two-story building with more than 8,000 objects. Yes, so the third research question is how do we, so as I've shown before, spatial reasoning about BIM models requires that you perform a lot of spatial computations in an order which inherently contradicts the declarative character of ASP in that a larger program is stateless. So how do we combine those kind of two different roles? And this leads to how I actually implemented spatial series solving for ASP for BIM and in this already off-the-shelf ASP system called Klingo. So spatial series, what are they? In this presentation, I will only limit myself to 3 major categories. So spatial series are implemented using a geometry database, spatial theory atoms, and spatial data structures. So this might not be easily understandable just when I'm going through the slides, but maybe we can come back to this during discussions. So ASP for BIM is a modified ground and solve program, which means that compared to the traditional Klingo or how the way that it has been implemented, ASP for BIM couples Klingo with spatial series. So the logical program talks dynamically with external data entries and computations. So first, a logic program is passed and transformed, so we can derive kind of like an ordering between different spatial computations. And then we use a spatial propagator to match symbolic atoms with numeric data, and to organize all those state-dependent spatial computations into a cascading series, so they can be executed accordingly to their dependencies. And then during propagation, we will also perform regular model checks to make sure that whatever we're deriving will be consistent with spatial theories. And we will also be, during propagation, couple the spatial propagator with a geometry database to compute spatial functions and to evaluate spatial relations on the fly, and to send those results back to the larger program to ground another segment of ASP. Yes, so geometry database, I've implemented this as a custom class that is called dynamically or continuously from the ground and solve process. I will come back to this later. So for spatial theory atoms, I used Klingel's built-in Python API to implement, to kind of define my own spatial terms. So for example, we can say that translate will be applied to a region plus a point, or scale will be applied to a region times a point. Difference will be applied to a region minus another region, this kind of thing. And in case of union, since it's a commutative function, then it will be applied to a set, an unordered set of regions with undefined length. And so in this case, the geometry database has those methods, those built-in methods defined, which will be used to compute those corresponding spatial theory atoms. And the second one is spatial data structures. In this case, we use sufficient and necessary conditions of certain spatial relations that are very, very costly to evaluate, to shortcut those unnecessary computations. So for example, if R1 is, if R2 is definitely not smaller than R1, which means that R2 is actually larger than R1, then we know that the part of relation will not exist, cannot hold between R2 and R1. So in this case, the size relation will be retrieved from a data structure that computes all the extents, which means areas and volumes of spatial objects. So whenever we're adding a spatial object to the geometry database, it also computes their extents and add up to an attribute in the geometry database that is implemented as a dictionary. And the second case is that when we know that the bounding boxes of two spatial regions are disconnected, then we know that then necessarily the regions themselves are also disconnected. So in this case, the topology relation is also retrieved from this spatial data structure that is constructed on the fly, that's called AABBs. Extents and AABBs are attribute to geometry database, which is kind of shared, which are shared attributes between the geometry database and spatial propagator. Yes, so finally, I will be talking about, yes, now that I've implemented or at least explained how ASP problem is implemented, I will demonstrate how it works in real life with the second case study. So yes, for this building, we need guardrails to be installed at leading edges. So for example, here and here. And first, so again, we're trying to define some spatial artifacts as the medium that allows us to communicate between very high level design requirements and very low level building geometry. So in this case, the spatial artifact is called fall space, which are regions a person might fall and injure themselves. So formally, fall spaces are the difference between the total site volume and the union of all slab elements. So in this case, we have a fact and a rule. The fact says that, yes, just take all the slab elements and compute a union no matter what. So because it's a fact, it will be automatically added to the model once the ASP4BEM program is granted. And this because the fact becomes true, which means that the head of the rule will also become true. So whenever the union of the slab is computed, we also compute the difference between the total set volume and the union of the slab, which gives us fall space. And it's kind of like in this way that we establish this order, that we try to pass the logic program first and trying to deduce what kind of spatial theory atoms are dependent, and we're trying to organize them into a cascading theory. So they're always computed exactly as you would have done in imperative programming. Yes, so the second type of spatial artifacts, but also mentioned before, is movement space. And in this case, movement spaces are the difference between the union of all slabs, which are the total walkable surfaces in a way. So the difference between union of slabs and the union of walls, which are kind of the total movement obstacles in a way. And so finally, this code is interpreted as fall hazard spaces which coincide with leading edges of a building or the intersection between movement spaces and fall spaces. Or formally, we can again have this this rule according to the ASP4BEM semantics that takes two predicates, and if they both become true, then the head of this rule will also become true, which means that fall hazard spaces will be computed, and they as highlighted here as the green regions. Yes, so this code I evaluated ASP4BEM on 4 different buildings with very different kind of typology. So ranging from 250 objects to 5,400 BEM objects. And ASP4BEM was also able to give us to identify leading edges or like compute the fall hazard spaces very fast in less than 1 second in most cases. And again, the results of those fall hazard spaces are also being validated by a construction safety expert who knows a lot about the physical state of these buildings. Yes, it took a lot faster than I imagined. So now I will just be talking about, yes, what are the take-home messages? The contributions of my PhD are kind of organized in response to my 3 different research questions. The first one, we want to declaratively query building models, and this is done by non-monotonic reasoning, which means that we can assert and retract knowledge as we acquire new information about the world. So this will give us this very declarative, very transparent character of the logic program. And the second one is that we're using evidence-based occupant modeling to assess buildings' performance, which means that how we interpret and how we compute concepts such as line of sight and access will be grounded, will be motivated and backed up by research literature about people, about movement, etc. So those metrics, those quantitative metrics that we're using are evidence-based. And the third one, how did we achieve that we could combine a declarative logic program with state-dependent computations is indeed by enhancing ASP with spatial background theories. Yes, so to conclude, ASP4BEM is used not entirely, so this presentation is only part of the research I've done, but in my PhD has been used for query and analysis about occupants, how they experience buildings. It has been used for model checking buildings against requirements. It also has been used for decision support to kind of make to help architects and engineers make design choices based on the outcomes. right? But AS4BIM has many limitations because it's a prototype software system, so it has not been widely used by practitioners in the industry. It requires still a lot of further studies into evaluating ASP4BIM in terms of, for example, portability when ASP4BIM is combined with other design and planning tools, or in terms of extensibility when ASP4BIM takes some existing ontology languages or semantic web or linked data, and how does that change the behavior of ASP4BIM, or in terms of scalability, when ASP4BIM is used in conjunction with normal clash detection programs, then how would that scale up to large-scale building models to thousands of requirements? That is still unknown from my side. And last, to which degree we can actually claim that ASP4BIM is transparent. If it's combined, if ASP4BIM is used in combination with some simulation or prediction or analysis program, what kind of explanation or arguments does ASP4BIM truly provide? So this is my favorite slides that I would like to talk about, maybe the limitations, the general inherent pitfalls of knowledge representation and reasoning, that it does assume that knowledge can be captured and formalized. But on the other side, we all know that human knowledge is by nature implicit, inconsistent, and fallible. And the second one refers to BIM or other information and data standards currently being used in the building industry, that they all assume that all the data or information should be gathered on a centralized platform, which has very little uncertainty, meaning that on this platform, all the information we put in should be correct and should be deterministic. But in the real world, it's rarely the case, as any kind of model are just an abstraction and reduction of the real world. Then there will always be some kind of imprecision, inaccuracy, and incompleteness in those models, which have to yet be addressed. Yes, so I would like to thank the Danish Independent Research Funds for giving me money so I could do my PhD. I would also like to thank my supervisors, Carl and Peter, for giving me guidance and to help me complete my PhD. And also a shout out to all my collaborators, Ali Akbar, Kamari, Johan Theiser, Olga Govina at Aarhus, John Fitzgerald at Newcastle University, Robert Amo and Johannes Timjadi at University of Auckland, Elif Jesset at NTNU in Norway, Christopher Rausch at Z Modular in Canada, Mani Pushpa at Auckland University of Technology, Said Talabi at Birmingham City University, and also special thanks to Jimmy Abu-Aldanian and Andre Borman at CHUM for hosting my exchange, Sivan Kipiki at LIST in Luxembourg for allowing me to run my workshop on code checking in last October, and also Torsten Schaub and Fred Wanko and just basically everyone at the Knowledge Representation Reasoning Group at University of Potsdam for giving us this incredible software system Klingo, and for giving me many advice on how to implement theory enhancement for space in Klingo. So thank you very much for your attention. Yes, and I'm on time. Should I stop sharing?
Thank you, Beidi. I think we can also stop recording now, right?